welcome to the 14th Taiwan young student thesis fight tournament. And today is the first fight. And we have 3 teams. We will probably take 3 hours to finish all the fights. Now, before we begin our tournament, let me introduce our jury. First, I am the chair of the jury. My name is Chen Hongyi from the National Taiwan Normal University. Second jury, Professor Cai Zhishen, also from the National Taiwan Normal University. And Professor Zheng Wenzhe from Danjiang University. And Professor Lin Jianhong from the Military Academy. And Professor Guo Fangqi from the National United University. Now we need a team. Each team, your team leader, to introduce yourself and all your team members. So let's start from the reporter.
Hello, we are Team Me from National Experimental High School. 还谢长汉，以专业有上在给大家一声。Thank you.
Opponents.
Honorable jury, delegates, we are team 赵美燕 from 台中明道中学. My name is Daniel. Wang Shenhe. He is Xiang Yu. He's Yao Wen. He's Chun Tao. And this is Tong Lin.
Reviewer.
Good afternoon, dear judges and fellow competitors. I'm the captain of Team Miracle. We're from Jinghu, Guangzhou. My name is Zhang Yachen. Xu Dezhong, Yang Youyu, Dai Zhirong, Zheng Yijun.
Now let's start our physics fight. According to these regulations, the opponent, you have 1 minute to challenge the reporter for the problem.
We'd like to challenge pedestal tower, which is problem 4.
Problem 4.
Pedestal tower is question number 6.
Number 6.
Number 6, sorry about that.
Number 6.
Yes.
Problem 6.
We would like to reject.
Okay.
So you have extra 1 minute.
We'd like to challenge force on an elastic, which is problem 11.
Problem 11.
We would like to reject the challenge.
Each team leader, please 他们还没有决定。
Okay, we'd like to challenge Trouble 13, which is handle power turbine.
Problem 13.
We would like to accept the challenge.
For each team leader, please write down your center on the blackboard. Now, the reporter has 5 minutes to prepare. Only one report.因为我们现在全部都变化了，他那边都有记，那当然这边也可以，只是说其实你也可以看清楚。他们在这种城市上面是什么？底下会所有主要的投币都会在下面的结束。那所以最后我们的评分也会列在全部都在现场都可以看到。他们城市现在都有写好。
Suspended above a candle starts to rotate. Optimize the setup have the gas equation right here, and then if we stretch it out, it would look like this. But if you see right here that our K, which is this one, is actually related to our width. So we can actually turn all the width related into K, so that in the end we can get a torque that should have a relation to K. So that's what we're also going to talk about later on in our experiment. And so considering the relationship between angular momentum and torque, we can get that the hot air which goes this way and the drag force which goes that way with minus and gap, and it would turn out to be the moment of inertia times the acceleration of angular acceleration. So we just said that this one should equal to this one. So this is when we feel it as if in this, but we can never mind about that. And then so we have our torque of hot air, which is what we're trying to look for, what we're trying to maximize in this experiment. And then so when airflow reaches balance with resistance, which is when our angular acceleration equals 0, we define it as a terminal so that this one can be eliminated as it is 0 right now. So we can get that our torque of hot air equals to this one. So that is what we're going to look for in our experiment, the angular velocity, the terminal angular velocity. Okay, so now moving into our experiment. So this is our experimental setup. So first, we have a stable environment which is indoor and low air conditioning, so that we make sure that there's no actual force active on it. And then also, we have the base section right here, which is used to stabilize the pillar and then also the spiral. So it's plate with the perpendicular to the table surface. And then we also have a power which is like a candle. So for each candle that we use, we try to make it into a symmetrical line so that there's no extra force, so that there is a symmetrical force active upon the spirals. And then the next would be this paper spiral drone. It is drawn using radial function, and then we print it and cut it in, and then it is also marked with tracking points. So how do we gather the data? So we mark tracking points and then try to analyze it mainly from taking pictures from videos from above. And then we chose a specific period of time where the spiral was in table spin, which means which equals to our terminal velocity. That's what we're going to talk about. So if we see the whole motion right here, this is the velocity of angle according to time. So we can see right here, but it is a bit messy, but we can see that there's actually a more concentrated velocity right here, and that also we have nearly no angular acceleration. So that is where we have the angular velocity is linear, so that there's no angular acceleration within its rotation. So this is when airflow interferes in mutualis, and which is what we call terminal velocity. So we have the parameters. First is the shape of spiral. Spirals are different with area of the spiral and strength of can power. So first, we're going to talk about the shape of spiral. So, well, we cut the spirals into different shapes, including circle, triangular, and then also square. So they all have the same width, and then these are the three shapes that we have. And then so by comparing the terminal velocity of the spiral, we can see that circle has a bigger angular velocity than triangle and then square. And the circle-shaped spiral had a more regularly and evenly distributed points, which is this, which I didn't put it on right here, but it told us that it has a more stable spin. So that is well, we didn't show the distributed points right here, but here is also the R squared, so we can kind of see that circle is a more fitted, has a more fit angular velocity. So in conclusion, we use circle-shaped spiral for the power experiment. And so why is that? Because we see like continuous surfaces right here, so that we believe airflow cannot flow through smoothly, which made it not so stable, and then that we have a lower angular velocity. Okay, so now we're going into shape to a different width. So we draw it with different radial function varying from 1 to 2 theta, so you can see it right here. So by comparison, we can see that angular velocity when R equals 1.8 theta, and then as we said in the theory before, we can see that K has a positive relationship to our final torque, and so which we expect it to go all the way up. However, we see that a drop in the symmetrical alignments with the candles. We use 2 to 8 candles, and then we use the same spiral. So with more candles, there is a larger angular velocity, but we cannot really see a linear form or anything there. But with more candles means more heat given to making the air pressure lower and making the air flow faster, so that we suppose that it generates a bigger force into making the spiral turn, so that it has a bigger angular velocity. And then in conclusion, so the spiral turns because of the outflowing airflow created by the convection that is heated by the air. And then we also have a friction tension to the tilted force in the surface of the spiral. And then a circle-shaped spiral has the biggest angular velocity and the most angular. And also the angular velocity peak at r when r equals 1.8 c/hour using spirals with different width. When the width of the spirals have the same, the fewer laps the spiral has, the larger the angular velocity it has when it's spin. And then that the more candles, the faster the angular velocity is. So in the end, we reach a conclusion that we should use more angles and use r equals 1.8 theta, and then also have fewer laps for our setup to maximize our torque. Thank you.
Alright, so hello everyone. So now I'm going to make some clarifications. So first of all, I'd like to ask, so for most of your experience, you use 2 candles, right?
Yeah.
2 sets of candles.
Yes.
Okay. So we didn't use 1. So we use multiple. Okay. And the next one, I would like to ask, how did the candle connect to a surface? How did the candle connect to the surface?
Do you mean we call it?
The ground. The ground.
No, it was just put right there, but the base was pretty flat. So
Okay, okay.
I can say it's very stable.
Okay, understand. Thank you. And I'd like to ask also, is the spiral suspended? Like, is it how is it touching the stick? So let's suppose did you actually make the center of the spiral touching the stick?
Yeah, so we particularly, it may not be really clear on the pictures, but we draw a little circle in the circle of the spiral, and then after that we start drawing our radius or function, so that there's a small circle where we can attach it to the
Okay. Okay. So did you make any folds while you're trying to stick it on the stick?
Yeah, we did.
Okay,
But
so
we
you
try to
did make
make
some.
it symmetrical.
Okay, sure. I'd also like to ask, have you taken into account the friction between the stick and the turbine?
We believe that it's too short compared to it's very short. It's very small compared to the other forces that it's acting on it.
Okay. So in your first experience, you were changing the mass. So did you
I believe that I changed the shape.
Oh, okay. So you changed the shape, but did you consider the mass? Are their
Yeah,
masses
so
different?
we try to make the area stuff, so we suppose that the paper is fun. It's all the same, right? So we try to control the area so that it's within the center.
So the mass is still a little bit different.
Maybe just quite a little.
Okay, got it.
start your presentation.
Okay. So hi, I'm Daniel from Team Endowment Mayhem, and today I'm going to oppose for the question Kendall power turbine. So first of all, the problem statement says that a paper spiral suspended above the Kendall starts to rotate. Optimize the setup for maximum torque. So obviously, the most important one is how you optimize the torque. And then secondly, I'm going to make some summary of the recorder. First of all, the theory that she used. The first one is convection flow, temperature difference, which is actually pretty accurate. The second one is, I believe it's pronounced Kaonda's effect, because it's probably a dark foreign language. Anyways, it predicts airflow state to a spiral. And the third one is, they stated that torque equals constant times omega squared. Oh, and then they also added that they should also minus the drag as well. And then they also define SA equals 0. So this is the experiment setup. They set up a paper spiral on a stick with 2 candles displayed. With 2 candles, which is more than 1. This is another point that I will be discussing with her. Also, parameters that she chose was different radius, width, shape of the spiral, and number of candles. Data, we believe that not enough data points were actually provided to see the check, so I will also be discussing that. For reporters, I believe that her advantages are pretty good. The first one is, of course, overall logic is very clear. She has clear data presentation and clearly understands the problem statement's requirement. And the presentation timing is also very on point. Some suggestions would be that she could probably speak more louder. Some terms are being skipped and undefined, which can be confusing. For her setup, her advantages were that she has a clear demonstration video. Control variables are being kept constant. However, we believe that 2 candles could create non-constant heat flow, which they didn't consider. And the second one is non-perfectly enclosed, and the third one is clay stick to a table, but did not measure the actual degree relative to the table. The fourth one is the spirals were handmade, and which could have made some errors. And also changing shape would lead to change in mass. So when they're changing the lap they did, or changing the width or the radius, they didn't actually consider the mass that was also changing. So they have mass changing, and they also have angle of attack that is also changing. For a theory, great explanation and easy to understand, and the theory fits to their experiment. Suggestions would be that she should consider the Bernoulli theorem for further analysis. We believe that that's pretty important. Drag coefficient is not calculated, and also friction should not be neglected. Experiment and data. Advantages are gathered at the end where the acceleration includes 0. She has interesting parameters. Suggestion would be could consider more parameters, and some terms are undefined, and some control variables were not controlled. So this is going to be my discussion structure. So I will start off clarifying some theory, such as variables that are not controlled in the experiment. And next, I will move on to setup and experiment clarification. So the spiral and state connection, the candle's number, the attack of the angle of attack. And finally, additional parameters that might affect the result. Yes, and I believe I can start the discussion right now. Okay. So overall, that was a really good presentation. But I would like to clarify some few discussion points. First of all, I'd like you to go back to the page where you showed your experimental setup. Above. Yes, this one. So as what I was emphasizing, the amount of candles. So we do know that from last year, one of the topics was synchronized candles. And we know that when you put 2 candles side by side, they will definitely affect each other. And what's special about that is that a vacuum space will be produced between the candles. So when you're adding more candles to this system, it's actually going to confuse the system even more, because you have to consider the interaction between the candles and all that stuff. What do I mean by that? So, for example, here's a very good example. This candle definitely has a higher flame, which might be producing extra energy, and this one has a lower flame. Well, this is only like a little point from this entire big problem, but it's definitely affecting how it's changing. So I would like to hear your explanation on why did you put more than one candle.
Okay, so we have, I have two explanations for that. So we actually tried to have two more experimental methods, which is one, we just put one candle right here, so you should not see this one. But in that case, the heat airflow would not be symmetrical, so it would only generate heat right here. And I do not believe that because we still have the barrier right here, so that this heat would not be fully transferred to this side, so that it would recreate a uneven slope. And the second approach that we tried was to attach a line on top of here, so make it's actually labeling instead of using a pillar. However, we believe that by doing so that in that case we can put a candle right here down below on the middle, right? But in that case we would not be able to. So in that case we would have to consider the torque that is created by the line attached to it when it starts spinning. So we believe that this is a more reasonable way to set up.
So I believe that I think there are a couple of flaws, or maybe I'm wrong. So first of all, the first reason that you gave was that this candle cannot be able to provide the entire energy for it to turn.
No, I mean it's not providing a symmetrical energy.
So you're saying that if this airflow goes up, then it will not make this this symmetrical turn.
Yeah, I mean it would still make it turn, but however you see that there is like a big barrel over here, and we also believe that in this case when there's a barrel, so when we did when according to synchronized candle, I think that you should create a vacuum system. What you said is should create a vacuum system right here, right? But we have a barrel right here, so we believe that we can neglect the
So I want to go back to your first explanation. So you're saying that this cannot go up. So this candle hitting this point will not be able to make it sort of like a reasonable spin. But if you go down to your explanation page, down a little bit here. So this is the hot air. So I believe from your explanation, this is only a small part of spiral. So the entire part of this is probably this big. So you only need, so from your explanation, you can only see that you only need one single airflow. And this single airflow will be able to provide it to spin.
Yeah, from this part it would sink it, but you have to also consider that for each small part of this candle, for each small part of the candle, a flow of hot air is believed is like extracts is pushing the spiral, so it has to have like a lot of hot air in order to push like a lot of small parts. So I wouldn't say it's only one particular energy.
But you do believe that one particular airflow will make it spin?
Yeah, well, make it spin from our experience. It's not spinning very smoothly. So like it returns to one point and then it starts to decelerate and then it starts to accelerate.
So you're saying that it will not be symmetrical?
Yeah.
Okay. Okay. The next question I would like to emphasize on is, would you like to go to your theory page where you calculate the torque?
This one? Or do you mean
The next one.
this one? Yeah.
The next one. Yes. So IA. Because I sort of missed out on this part. Do you believe that this one calculates the torque for the entire spiral? Is this what you mean?
I would say, yeah, it does include. It would be like say the whole torque graded for the spiral, but what we're trying to define right here, so what we're trying to maximize right here from our definition is actually the torque of the hot air, because it's the candle that is actually pushing it. So we believe that by calculating the torque of the power generated on it, it's more like reasonable way to calculate.
So you're basically calculating the torque torque generated by the handle, and you're saying if that torque reaches maximum, then you're maximizing the torque of the entire system. Is it? Oh, okay. So I think you got it pretty accurate because I believe that when if you are using this to calculate the torque of the entire spiral, then it might be a little bit wrong because when your spiral eventually reaches terminal velocity, which is required by Jordan's statement, there will not be an acceleration, which means that you will not be able to predict the torque by using this equation.
Yes,
Yeah.
that's why we said it's with zero.
Okay. So according to your setup, this is basically like your spiral, and in the center of that, in the center of the entire circle, that is, so you cut through this, right?
So it's more of like you do not leave a small circle, right?
So how did you stick your sticks through? Did you simply put it right in the center
We
of
do not
the?
stick through it. We just simply
Put it on.
make a hump and put it on top.
Okay, so you cut basically through the center, and you still put the stick in the center.
We did not stick through it. It's just
Yeah. I know.
Yes.
So basically, you have the entire circle in the entire spiral, and you cut through this. So you have to know that this point is cut. Then how do you put your stick right here? Because this one should be broken apart. So
It's not that we cut through it. It's that we leave a space area.
so then you so this area still has paper, and you directly put it there. Okay, then that makes more sense. And did you sort of make any folds? So I believe that I heard you said that you made some folds to it.
Yeah, so basically the syntax structure. Fold it back up, fold it that way, and we put it on.
Okay. Then do you think the friction between the stick and the spiral will affect the entire system? Because while your spiral is spinning, I think that might create some friction, which might be somehow relevant to your.
Yeah, I do agree that there must be a friction of during the system. However, the first part is that because we're using a pillar which is really pointing on top, so it actually has a really small traction point. And then the second part is we all know that friction is related to it's related to normal force, right? And then we believe that the paper is actually very light, so that the friction, which is
Will not be less.
will not be less.
Yes, agreed. I would now like to move on to your first experiment. So in the first experiment, these three spirals that you made, you said that their masses were pretty much the same.
Yes.
Okay, so that's a good thing to hear because you consider the mass that will probably affect the result. But I'm wondering if you consider the angle of attack because we all know that each spiral will extend to a different length, and when you extend to a different length, the size of the spiral might be varying their angles. Because if you extend it even more, the angle will be very obvious. But if you didn't extend that much, then the angle will be pretty fast. Did you consider this?
So that is part that we neglected, but however, if you see right here, we gave an explanation of how, why, but if you see actually right here, it's a continuous surface right here, so we hardly believe that it can be quantified each type according to the spiral.
Okay. So I believe that's probably a major flaw in your experiment because you didn't consider the theta, which is very important because you have to consider the angle.
Upon you need to stop your special.
Okay. So overall, I think that was a pretty fruitful conversation. We did a lot of explanation and also clarification. But however, I think some major flaws were that she didn't consider probably some of the variables or some of the parameters that might be affecting. So for example, like what I just mentioned, the angle of attack, which varies a lot when you're trying to let a spiral spin due to its force. Okay, so we have they really did a good job of clarifying many parts of the presentation, and they tell us that the details details of experiment theory, equation, and their perspective on their experimental setup. So I believe the only thing that they can do probably improve on is probably on their experiment. And thank you, that's pretty much it.
Now, reviewer, you have 3 minutes to ask questions to reporter and the opponent. Please step up and please put on your mask.
Sorry.
Oh, at my time. Sorry. This is a reviewer from Team Miracle. I'm John Xu, and I will be reviewing the problem candle power turbine. First, for the review for the report, what do you think causes the shaking in your experiment? How do you explain?
Because so I think it might be because of that. The candle might so we're actually hard to control the stableness of each candle, right? So each candle might start to glow, it starts to go small at any time. So we believe that might be so we in continuously support energy providing is what causes
Okay.
to shake.
So do you think all the flow airflow will be laminar flow, or will they?
So we actually try to see if it's actually laminar flow or turbulent flow using the Schiller method. But however, we really cannot really. It's really hard to put it into experiments. So we try to examine if it's turbulent or laminar.
For the opponent, do you think that the turbulence will affect how the candle will be?
I think another point that will definitely affect is because the uneven distribution of mass from you can see pretty clearly that is pretty wobbly. So if you apply a flow, I think that will wobble no matter what.
Okay. Next, in your experimental setup, you change the candle power and then the distribution, like how the candles are distributed at the same time. Do you think you can separate it like those two?
I would say it's very hard. So the only thing that we try to do is make it into like a point symmetrical. So that you can see all right here that now has a symmetrical line.
So you're gonna change, you're gonna like hold the candle power class and then change the distribution of the candle.
I think it would say
Okay. How do you think the Kawaii effect will look like turning turbine? Do you think it will increase the torque?
I think it's well I wouldn't say it's increasing the tone, it's actually providing.
It's actually providing. Okay, what's the you want this?
Okay, well, thanks for phrasing.
How does the Kawaii effect affect the turning of the turbine?
I think it definitely affects the spinning of the turbine because the lower pressure on the lower side will definitely push the spiral to spin toward the other side which has lower pressure.
Have you considered like the drooping of your spiral?
Hands up.
Okay.
Thank you.
honorable judges and fellow competitors, this is the reviewer from Team Miracle. Okay, let's start from the problem statement. Okay, the key questions we believe are how to maximize for the reporter, they demonstrate a phenomenon, and for their theory, they consider the convection, Kalanda effect, resistance from friction and air drag. For their experiment, they tested different shapes, different areas, and different numbers of candles. At the same time, they changed different distributions of candles. For their probe, they had clear analysis of the drag force. They considered a variety of parameters, and they had good time control for their presentation. However, they did not analyze the shaking of the spiral. They did not analyze rotational acceleration. They did not control the drooping of the spiral. They changed two many variables at once, namely the distribution of the candle and the candle power. And also the drag theory only works with laminar flow, and they did not consider turbulences. For the opponent, they mentioned the theories provided, and they provided other theories such as the Kalanda and Bernoulli theory, and they gave many suggestions. They pointed out that they had no drag coefficient. However, they did not mention the error in their presentation. Okay, on to the discussion. The first discussion topic was, why are you using two candles? The reporter said, try other setups, but this setup provides symmetrical torque, which is more stable. The reviewer thinks that the reporter should definitely consider the effect of two candles, since their airflow affects each other, and the flow field is definitely more complicated for more candles. The second discussion point was that there were only one airflow push the whole spiral, and the reporter said every part of the spiral will receive airflow, but they believe that one airflow can push the spiral. The reviewer thinks that they should consider how to change the candle distribution and also the power provided at the same time. And the third thing that the opponent talked about is how the angular acceleration caused by torque in the candle. The reporter said, yes, there will be effect, and the reviewer thinks that this question is trivial and that the opponent should focus on more important questions. As for the connection between the spiral and stick, the reporter said it is left on an area on the top of the spiral, and the reviewer said it is a trivial question too, since it was explained in the presentation. And the opponent asked about friction between the stick and the paper. The reporter said that friction was small, so they think it's insignificant. The reviewer thinks that the torque is small because addition from the friction applied torque is also small. Lastly, the points missed. We believe that they did not discuss the effect of turbulence. They did not consider how to keep the spiral from deforming. Since if you droop the spiral, it starts drooping, and the distance between the bottom of the spiral and the candle is changed. And also, there are no theory for quantification of the torque from the candle. The opponent skips his discussion on Kalanda effect, and no discussion on the error in the initial angle acceleration graph. And also, they didn't discuss the changes in candle distribution and the candle power at the same time. Thank you.
Okay, so I'm going to start for the discussion. So first, we have multiple panels, which we believe that it's more symmetrical. As we said, we still agree with the opponent and the reviewer that maybe we can consider more factors into that, and then to consider your equation. Yeah, that being said, and then also how is this? So we still believe that friction is small enough to neglect, and then we're happy that the others also agree with us too. So different data of the spiral. This was a question that we did not fully answer before. So the triangle and square were hard to keep the same as we see the continuous surfaces of it. But we can see that in the circle-shaped spiral, there is actually a more continuous surface, and that it's easier for us to keep all the theta same. So that's why we only use simple spiral for the best experiment. So I believe that can be neglected for the experiment that's come afterwards. So we left out is the airplane turbulence are unknown. As I just talked about before, we already examined the variables, but it's hard to consider in our equation, though we do believe that there is actually a way for us to
questions of the jury. And reviewer, please. Any questions?
Question for three of you. When you do this measurement, where do you see the error line come from?
So I believe that despite that we try to keep our environmental conditions the same as the reviewer and the opponents said before. Maybe it was careful that the unstableness of the candlelight may cause a little bit error in this case of the experiment.
Yes, I agree with.
Okay, so I pretty much believe that the wobbling of the spiral might pretty much cause a lot of significant errors in her experiment. And also the fact that she didn't consider the flow, or which she said that it was they detected because it was not significant enough, but we think that it should be also another error. Yeah.
Okay, I believe that I agree with the reporter and the opponent that there might be two sources of error. First, there is a shaking of the spiral because of their external setup. And secondly, there are turbulences in the air that they might not be able to control.
Please, page 14. 14.
Yeah.
Okay, I also curious about the equation. Why the I and the alpha when you explain it?
So I would be the moment of inertia of the spiral, and then the alpha would be the angle of acceleration towards the whole motion of the spiral.
Okay, so I you explain what is the I in this dynamic. About which parameter, maybe mass, maybe radius, or length.
So it's both related to it's all both related to mass and radius, but it's also related to the structure of the spiral. But however, as we see, because we're trying to reach a terminal velocity here, which will turn so the angle of acceleration should equal to 0. So we believe that the eye of the spiral will not affect our whole equation as we turn this into 0 in the end.
So just relation to the mass.
In radius.
Okay. Yes, the radius. Thank you. And the review. You see, you just do the experiment with the laminar flow, right? Laminar flow.
I believe there are lambda and turbulence.
Okay. And do you think it's supposed to change to turbulent flow in this experiment easy to do? So I think you think laminar flow. Yeah, just do this. You didn't do just laminar flow. But suppose we change the heat.
Sorry, can you rephrase it? Yeah.
Yeah. Suppose you change it. Do you think it easy to do?
What do you mean changing the
Turbulent
laminar?
flow.
Just changing the laminar flow into turbulence.
Yeah.
You mean the effect on the
Yeah. Or maybe a bit or not.
a spiral, like turbulence. It might not like spin that well, that stable. It's turbulent.
Well, it's stable.
Yeah, it would be less stable.
I think that's what makes her experiment. So for a final day, there were a lot of a lot of ups and downs, and I believe that that's because there were a lot of turbulence. Yeah.
We also did realize the problem that turbulent flow may have an effect on our experiment. So that's why we try to see if we can examine if the airflow produced by the candle is laminar or turbulent by using the Stiller method. But however, we cannot really conduct the method.
Not easy to control.
Yeah, it's hard to do.
Yeah.
More questions? First, the score for the reporter 8-6, 8-6. Now the score for opponent 8-7-7-7-6. The score for reviewer 8-7-8-7-7. Let's everyone. We finished the first stage, so we will have a 10 minutes break. Opponent, challenge the reporter.
Challenge problem 12, strength motion.
Problem 12.
We'd like to recheck.
Richard.
We would like to challenge problem 15, boycott effect.
Problem 15.
We'd like to accept the challenge.
Accept. Team leader, please write down the center on the blackboard.
everyone. My name is Daniel, and I'm here representing D121. And today, I'm going to report problem 1545 effect. So the problem statement say that particles are suspended in a liquid that has a lower density than the particles. The particles will settle to the bottom of the container, and the rate of settling can be affected by tilting the container that holds the liquid. So we have to explain this phenomenon and investigate how the effect of relevant parameters. The key points of our entire experiment will be particle density and the angle of tilting the container. The discussion points will be the rate of the accumulation. So this is our problem statement demonstration video. So as you can see, because this is sort of has lower quality, but okay, stop. You'll be able to see that at here, most of the particles have already descended, but at here it's still in a very muddy situation. So basically, this phenomenon implies that when you're tilting it at a specific angle or at a specific range of angle, the particles will actually descend much faster than when you set it upright. A very simple fundamental explanation for this is because when it is tilted, there will be a pure water layer that will be created, and through that pure layer of water, there will be a global convection going on. So this one has normal particle velocity, and this one also has a normal particle velocity going down. However, the difference between the two is because this one has a global convection that pushes and accelerates the entire movement, while this one doesn't have. So this is how we define the different areas. A is the interface between the particle suspension layer and pure liquid. B is particle suspension layer. C is pure liquid layer. So it is through C that the global convection is allowed. D is the accumulation layer of particles at the very bottom. A, alpha, it's a little bit special because we're defining the angle of inclination from the vertical axis and not from the horizontal axis. Height is the height of the suspension layer. So the suspension layer is lowering at time, so it is not a constant. So it is h of t. It's actually a time equation. For B, it's the width of the cylinder. The theory that we use is P&K theory. So this theory basically calculates the rate in which a pure liquid layer is created. So by calculating this value, it reveals the rate at which the particles descend. So this equation is pretty much very simple. V0 is the initial velocity of each particle, and when you times it with this length, and you plus the initial velocity times the h tangent length, which is this one projected onto the horizontal axis, you'll basically get the rate in which a pure liquid layer is created, and this is how we simplify it. And keep in mind that the h we use is, as mentioned, h of t, because the h has been always changing. This is how we set up our experiment. We have an RSN, and atop on it there is a clamp that holds the test tube, and we have a rubber stopper to stop the liquid from overflowing. And we basically set a high-speed camera in front of it. This is our hypothesis for our experiment 1. So for dependent variables, we're basically finding the sedimentation time. For independent variables, we're changing the angle of inclination. So this is our first experiment, which is changing the angle of inclination. The values we'll be testing are 10 degrees, 20, and all the way to 80. We'll also be doing 45 as well, as it is a very special angle. So our hypothesis is that as the angle is increasing from 10 to from 0 to 45, the descending time decreases. This is because larger pure water layer that allows stronger convection currents. Our hypothesis from angles decreasing from 45 to 90 is that the descending time decreases. With increased angle comes lower acceleration down the direction of the test tube. So this is our hypothesis based on our previous observation. These are the control variables. So when changing angle of inclination, this is how we get our theoretical data. The Vt, which is terminal velocity, is calculated by Stokes law. So this is how our theoretical value looks like. And the red dots here are the experimental values. So now we'll move on to the discussion. So first problem we observed was that is 80 degrees when you're tilting this bar, is this really the optimal descending rate? Is this really the fastest rate at which the particle descend? So that's our question. So our definition of fully descendant is when particles amount at the bottom doesn't seem to change anymore. But when in 1.4 radian, the particles get caught up on the side of the tube and doesn't move down anymore. So this is what I mean by how they get caught up. So normally all the particles should be descended at over here, but because this angle is a little bit too slanted, the particles have a shorter settling distance, which isn't what the problem statement asks for, because the problem statement is asking for it to settle fully, but this is definitely not settling to the fullest because this is settling on the side. So therefore we reviewed the footage and found out that after 1.2 radian, which is 70 degrees, the particles will get caught up on the sides. So before 60 degrees, then they are having a perfect sedimentation because they all fall down to the bottom. But it doesn't fall down to the bottom after 70 degrees. So we predict that we will be neglecting the trials after 70 degrees, as it is not what the problem statement asks for. So our conclusion is that 60 degrees, which is 1.05 radian, about 1.05 radian, is the optimal setting level. The second problem from the first experiment is that there seems to be a quite variation between our experimental data and theoretical data, although they basically follow the same trend. And our explanation for this is that there were too many particles. The PNK theory only calculates the particle sedimentation time when each particle is viewed as individual particles that are settling. So it didn't consider the fact that each particle will be actually colliding and collision. When collision happens, it basically slows down the descending rate because each particles will have to spend a lot more energy and time on bumping into each other, which the PNK theory doesn't consider. So this makes us wonder, maybe we should find a range at which the PNK theory is valid. So we set out to find the Reynolds number. So Reynolds number basically helps determine whether using PNK is valid or not. So here is our second theory, which is Reynolds number. So we believe that when Reynolds number is larger, the sedimation velocity of the single particle is larger. But although the convection behavior occurs earlier, which means that it should supposedly descend faster. However, it has little effect on particle acceleration due to its increased size because it's too large and it collides with each other. When the RE is too big, the descent actually is slower. They descend actually at a slower rate. So thus, we predict that RE has to be closer to 0 for PNK to be valid. Because when RE is 0, it means that each particle is viewed as individual settling, which is what PNK predicts. So now we will be setting off to find the range for a Reynolds number for PNK to be valid. Our experimental 2 will be changing the amount of particles. The dependent variable is still the same, sedimentation time, and the independent variable will be mass of the particles. So we will have 2, G4, G6, G, and 8G. And correspondingly, their Reynolds number are as presented around 122 and so on. So this we conduct to three significant figures. Our hypothesis is that when RE equals 0, RE approaches to 0, PNK is valid. So we predict that 2G will follow the trend closely. So this is our first result when we set the angle at 50 degrees. We found out that there's actually a very special thing when RE is at 609. So when RE is at 609, it doesn't seem to be following the trend. So might this be the range at which PNK is valid? Because as we can see, when RE reaches this amount of number, it is not following the trend anymore. So we set out finding at different angles. We find it at 10 degrees, 20 degrees, 30 degrees, and 40 degrees. And what we found was that all of them, when the Reynolds number approaches to 600, when all that approaches to 600, the PNK theory doesn't seem to be able to predict this value anymore. So we predict that the range of the real number for PNK to be valid is likely at 0 to 500. So this is our conclusion. So from experiment 1, we found out that the experimental values follow the theoretical trend, which is a very good sign. But however, it lies above the theoretical values, so there must be a systematic error. And our explanation for that is there were too many particles, causing larger Reynolds number. And when larger Reynolds number is appearing, it means that clotting and collision will be happening, and in which our PNK theory doesn't apply that. So we set out to better this PNK theory by finding the suitable range for PNK to be valid. So it is certain that when RE approaches to 0, PNK will be valid as they are being viewed as individual settling particles. But what's the range for it? So that's the purpose for our experiment 2. So from a couple of experiments, we found out that when RE is between 0 and 500, it is perfect that PNK will be able to predict that the entire system is valid. However, when it exceeds 500, PNK cannot predict the outcome anymore because of turbulence and other problems that we did not find. Yeah, and that is basically our presentation. Thank you for your attention.
Thanks to reporter for his presentation. I just have to confirm, you said that experiment 1, 15 degrees is fastest attenuation rate, right? 15 degrees. What is the fastest attenuation rate?
We believe it's 60.
60 degrees, okay.
That's 60.
Okay, so second question, is the velocity of an individual particle enhanced? So not just the settling rate is enhanced, the velocity of an individual particle.
We believe that it does not change.
It does not change, correct. What is the viscosity for your first experiment?
So it's basically the viscosity of water.
The viscosity of water. And what's the particle size?
Particle size is between 1700 to 1800. Is it millimeters?
No,
Yeah.
You were able to observe the clear top layer of the sedimentation. And that's how you measure the sedimentation rate.
Clear top layer.
You're able to observe how the top layer descends.
Okay. So that's basically based on our definition of each.
Okay, thank you. And can you go to page 15? How did you find the red dots? Because
okay, so experimental value. So we basically set up a camera and we reviewed the footage, and we based on our definition, it is when the bottom layer doesn't change anymore. So we reviewed it frame by frame, and we figured that the bottom layer doesn't change anymore, and so that's how we got the red dots.
Alright.
Yeah.
But,
So
but if you're only observing the bottom layer, how do you get the data? What is the value of the data? What is the value of the data represent?
the value of the theta.
The data, yeah, you're only observing how the bottom layer changes. Okay. Okay, that's okay, thank you. Good afternoon, dear judges and fellow competitors. I am Zhang Miracle, and I'll be proposing problem 15 effect. So the problem statement says that if particles are suspended in the liquid that has lower density than particles, they will fall to the bottom. And the rate of settling can be affected by filling a container. The reporter says that the rate of settling is affected, is increased when the filling angle is increased within a range. And the reporter says that, yeah, that was just what I said. When the filling angle was increased, the settling velocity was increased. And they use PMK theory, which states that when the filling angle is increased, the effective settling area is also increased. And that's their intuitive explanation. And also, in their experimental data, they said that the best sedimentation degree is 60 degrees. And they also tested that when the Reynolds number is between 0 to 500, PMK theory applies. And the purpose of this presentation is that we provided an intuitive explanation where it explained that tilting increases the effective settling area, which also increases the settling rate. We also recognize the limitations of PMK theory. You change different parameters such as control the dimension in this group Reynolds number, and also change the tilt angle. And he has good time management using every second of this presentation, and he has a well-structured report. But for the cons, he does not verify the range of PMK theory, and I'll explain that later. It doesn't provide enough experimental details. For example, if you change this Reynolds number to a very large number, for example 500, then the particles would descend very quickly, and there wouldn't be a clear top layer for him to observe. So he didn't provide the explanation of how he observed the settling rate for large Reynolds numbers, and he has an unpersuasive theory explaining the error between his theory and explanation when the Reynolds number is large. And he does not thoroughly investigate the phenomenon, and I'll explain that later. The points to be discussed. I'd like to discuss what may cause the best sedimentation angle. Because PMK predicts that when the tilt angle is larger, the sedimentation rate will also be larger. So I would like to hear what the reporter has to say about why PMK wouldn't apply. And second, I would like to discuss what the effect of Reynolds number on settling is. Thirdly, I would like to discuss if the velocity of individual particles is increased. And fourthly, I think I have a way to explain the deviation between your experiment and theory on page 17. And then I would like to explain we would like to discuss the effect of particle concentration on the settling rate. And the reporter's explanation is that collision happens, which decreases the settling rate. And for experiment, we would like to discuss how the viscosity changes the thickness of the clear fluid layer, because the reporter says that the thickness of the clear fluid layer is very thin and it doesn't vary substantially with time. Okay, so I would like to begin the discussion. So, were you able to observe the thickness of the clear fluid layer?
Okay, so I'll explain how we experimented our experiment. So,
I asked you if you can observe the thickness of the
we did not observe the thickness of the pure liquid layer because that is not what we are looking for. What PMK predicts is that when it basically calculates the rate at which the sedimentation layer, the pure liquid is formed. But what we tested was the time when all particles fully descended, and that time is basically the same as the rate at which a pure liquid layer is created.
Thank you. Can you go to the page where you presented your data for a large Reynolds number? You said that the settling rate was lower than PMK prediction. Page 17. You said that? The red dot is the experimental.
Oh, okay, sorry. It's the experimental. Yeah, it basically lies above the theoretical value.
So what's your explanation for this deviation?
Okay, so like what we just mentioned, because when at 4G, the Reynolds number is reached over 600, like from our later experiment, we found out that it probably reached over 500. So by reaching over 500, it starts to collide into each other. But I know it follows the PMK trend.
So you change the Reynolds number by increasing the particle density?
No, we do not change the Reynolds number.
Oh,
It's changing the mass.
Oh,
Because Reynolds number is directly
Can you write down your equation for the particle's velocity on the blackboard? The Stokes settling's velocity.
Is right here.
Okay. Yep. Because can you go to the blackboard? So the settling velocity can be explained by that equation, but the settling velocity, the particle of an individual particle is also affected by the particle density. When the particles are trying to fall down in a container, an equal volume of water has to flow up. So that motion of water creates a drag on the particles as well. So Stokes' law only works for low particle concentrations. If the particle concentration is most large, you have to consider the flow of water that has to replenish the individual particles. And the experimental formula for this flow is that you have to multiply the Stokes' law by 1 minus c to the 5th power. And that is the correction for particle density. And this can also explain why your settling rate is lower for higher particle density. Do you agree?
So C is basically a constant.
C is the particle volume factor, sorry for that. It's how much volume your particle takes up in the higher container. Okay. And also, the pure fluid layer remains thin throughout your sedimentation, correct?
So according to our definition, pure liquid layer isn't only the thin part; it's also the flow.
Yes, exactly. But for the pure fluid layer close to the outer boundary, its thickness remains relatively constant. And that is why you're able to use the Kinget theory.
Yes.
That's just a preliminary condition.
Yes.
So your explanation is that when the particle settles, the water comes to the clear fluid layer and it flows out.
Yes.
So because there's a large velocity here in the water and the clear fluid layer is thin, the velocity gradient here is also very large. And because there's a large velocity gradient, it may also cause a viscous drag on a nearby suspension. Do you agree? So this viscous drag will cause the particles to be dragged out.
Yes.
Okay. And using this, can you explain why there's the best? Can you explain why there's a best settling angle? Why 60 degrees is the best settling angle for settling? Why 60 degrees is also the best for settling?
That is because from our TOK theory, we can find out that because you project the standard side onto the horizontal side, when the angle gets, so basically it's this angle. So we are projecting this side onto the horizontal side. And basically, when you project, when this angle is larger, the value basically gets smaller. So that's why we got a chart like this. So basically, when you increase the mass of basically when you increase the tilting angle, that's why it increases, because the cosine of this angle is actually getting smaller.
So you're saying that the settling rate depends on this height?
Oh, no, this angle.
This angle. Wait, but I thought it only depends on this affects the settling area. And I know that is affected by this angle, but your theory doesn't explain why 60 degrees and settling rate.
But our theory allows us to basically predict the entire experiment theoretical value. So that's how we got basically the
Yes, but why is 60 degrees fastest instead of?
So actually it's 80 degrees. That's no, it's 80 degrees. That's fastest. But I don't know if you weren't listening or what, because we clearly described that after 70 and 80 degrees, they basically settle on the side. So we basically neglect 70 and 80. So this should be the largest. So that's why we have this theoretical.
So your reason is actually up to the range of 80, and it should also continue, but most of your particles is settled for this.
Yes, and that is not what the probability of passable.
Okay, but you said that your thickness of your fluid layer remains relatively thin. How could the thickness of it remain relatively thin if most of the particles have settled onto the bottom basic wall? You couldn't apply PMK to 80 degrees, like you said, because most of the particles have fallen to the bottom basic wall, and the thickness of the fluid layer changes.
Are you saying that pure liquid layer changes?
Yes.
Yes, because basically, so at every angle, so we know that this is here's the angle, and we basically project this one onto this. So it's basically calculating entire part was set in grit.
Yes, but you also said that. No, I'm asking you about how the thickness of the material fluid layer changes, and you said that above 80 degrees, most of the particles have settled to the bottom facing wall. And doesn't that mean the thickness of the material fluid layer changes?
Okay, let me explain PFK theory again. PFK theory basically, where's mine? So PFK theory is basically calculate when you project this side onto here. So in which every single experiment, the theoretical value changes because alpha is actually increasing. So our theoretical value actually varies, and because this calculates the height of the utmost layer, it is actually predicting that the thickness of the pure liquid layer is actually changing by time. So we did consider that the pure liquid layer at the side is actually.
Well, if the thickness of the pure fluid layer is changing with time, then the B term here will also change with time because B is this width here.
No, B is the entire width.
Yes.
This is the entire width of the.
But the effective settling area is from here to here, and it does not include the clear fluid layer.
No, but from this, because we are neglecting, not neglecting, from here, from this part, we can see that when we use B H over B, so this means that we are actually considering that this entire volume is actually contained with all of the particles.
But this here changes, so B does not stay constant.
Yes,
I'm not sure.
no, B is always a constant. B is always a constant.
But that tells me that you don't really know what PFK is telling you. PFK tells you that the effective settling area.
You know, this is B. So B is basically the entire length. And the reason why it always remains a constant is because PFK predicts that all particles will eventually descend above this line. So basically, the P will always be constant. So P will not be a function of time because it will always have particles right here. So that's why we said that.
Why would it always have particles? Can you draw the settling vessel for a really large angle? For example, maybe this is about 75 degrees.
Yes.
So this here changes. The top of this settling layer changes. So B does not stay constant.
Yes. So that's why we adapted over 70 degrees. Because, like I mentioned it a couple of times, when over 70 degrees it descends on here, and on the side is not what the problem statement asks for. So when under 70 degrees, under 70, let's say this is 60 degrees, all of the particles have already descended on here. So that's why B is always a constant. It will not be a function of time. It will not leave this length. So I believe that part of your probably misunderstanding what the PFK value is.
Okay, I have a suggestion. I think you just find the top of this layer here.
Yes.
And maybe using that will help you quantify the settling rate.
Yeah, but yeah, this is exactly the problem that we met because this entire area is hard to calculate. So that's why we did directly neglect it because it is not following PFK and it is also not following the problem.
Well, we think you don't have to calculate the area, you only have to know where the position of this here is because.
So you're saying that basically calculating the position of
If you want to know the height, the rate of change of height, not the rate of change of the volume.
Time's up.
Okay, thank you. So the reporter agrees with our suggestion that they can use the Richardson-Donkey experimental formula, that is the 1 minus c to the 5th power there to explain the deviation between this experimental values and theoretical values for particles with high particle concentrations. And we also discussed the effect of the clear fluid layer on the sedimentation. And the opponent thinks that they should consider how the thickness of the clear fluid changes with time, and they said that they neglected it for angles above 70 degrees because most of the particles have settled to the bottom facing wall. And thirdly, we discussed that we discussed the way to measure the settling rate for large tilt angles, and we proposed that you can measure the height of the settlements, the top layer of the height of the settlements. And Yes, and then the report agrees with our suggestion.
Okay, so I have a few questions for both of you, and please give me in short answers. So first is for the reporter. How do you add your particles?
Add your particles.
Yes, into your liquid.
So this entire volume is basically concealed. So it is
Okay.
always in the,
Do you think that the initial conditions of the particles, which is like the original velocity or angle of your particles, affects your result?
the original velocity? No, because the PFA theory, so this is actually terminal velocity. So only terminal velocity affects, so not initial velocity.
Okay, so I would like to ask in A20.
Okay.
So is the Reynolds number considered an atmosphere?
No, this atmosphere is actually in the liquid.
Okay, so how do you get the Reynolds number? Like you just put.
Yes, we just input the number because these are all constant.
Okay, so can you both give me a one sentence explanation of the phenomenon?
So the fundamental explanation is that there will be a global convection inside the tube.
Global convection.
Yes.
And the effective settling area is increased, and and the formation of the clear water provides a pathway for the water to access to the top.
Okay, so what triggers the global convection?
Because the tilted there will be a thin pure liquid layer that allows, as the opponent is through, there will be a cinder where water goes up and then pushes.
Okay, so by that, how do you define clear and pure?
So from this, we have a paper definition. So pure, we observed it from our video footage, but there will be clear divisions of each layer because the top layer will be the clearest, and the second one will be very muddy, and this is very observable.
Okay, so do you think the shape of the tube affects the convection? Like in page 5, this is a square tube, but
Yes.
you still use a tube with a curve. Do you think that affects the global convection?
Yeah, I think that definitely affects it, probably because the bottom is a curvature, and that definitely affects how maybe there will be a turbulence or something because it is not a flat surface.
Both of the reporter and the opponent, I would like to ask, do you think that the particle's velocity has changed during the whole convection?
Yes, the velocity of particles have changed, so that's why we have the terminal velocity.
And then yes, also that particle velocity changes according to its position.
Okay, thank you.
Thank you.
Okay, I would like to start. So I'm Xie Chen, I'm from TV, and I'm the reviewer for the boycott event. So here's the problem statement, which we need to make focus on the second rate and other parameters. So first, for the reported, the the summary of the phenomenon is that the tilting of the container will result in larger particle settling speed, PNK theory collision, when 60 degrees, there's a fastest speed, and Reynolds number 0 to 500, and PNK applies. And for the experiment, he did angle of inclination and amount of time. For the pros, he explained the boundary condition for experimental data clearly. He had clear logic for the report and well-structured report. So for the cons, he did not give clear physical explanation of the phenomenon which the problem statement asked us to do, and he did not define the specific terms of the report. Observation video is not clear enough for us to know the whole process. He did not fulfill the task of the problem statement, which we say he did not explain the phenomenon in this report, and there's not enough parameters to consider, which there's only 2. For the opponent, the pros are he gave alternative explanation to a deviation, he provided more possible parameters, and clarified definitions. But for the cons, he did not help clarify the explanation of the phenomenon, which is lacked through the whole process. And he spent too much time on a single question, as he was trying to say that the Stokes law can apply when the concentration is high. So for the first discussion, is the reason of the deviation. The report said that there's a difference in the Reynolds number, and the opponent said there is a correction term for the Stokes law, which will not describe the deviation. So for the review, we agree with the opponent that there is a limitation towards the Stokes law, so PNK would not fit completely right here. So a correction term like 1 minus v5 squared can be considered right here. For the next discussion is the layers of liquid. The reporter says that V should be considered as a constant according to the PNK theory, but the opponent says the V of the PNK theory should be irrelevant to time. When most of the particles settle to the bottom, the clear layer cannot be considered very thin. So for the reviewer, we think that according to the picture, the report showed the bottom layer is not actually a constant, which we agree with the opponent that we should clarify that in PNK theory. Clarify that in our investigation. So here are some points which is a clarification of the specific term, the physical explanation of the phenomenon, and origin of the PNK theory is not mentioned. He just gives us his equation, but he did not tell us why PNK theory fits into this experiment and has to do with the whole process. And he did give the reason of using this theory. And last is the terminal velocity, which we did not see clearly because he just told us that as all the particles settle to the bottom, he did not mention about the whole process of settling, which is considered the settling rate. And second is the definition of clear and pure layer is not very clear. He just told us that, as we can see, it's very clear on the top, but we think that should be clarified. So this is my report. Thank you.
Okay, so this is my concluding remark. So first of all, let's start from question 1. So the opponent asked why is 60 degrees the best identification rate? And we said that through the theory explanation, we can see that over 60 degrees the particle descended on the side. So meaning that we can directly neglect them because that is not what the problem statement asks for. Problem 2, why is a clear fluid layer relatively thin when there is larger area that is descended? And why can you still use the constant B? And this is because that the PNK theory shows that the particles will descend to the bottom, and where the coefficient B will stay constant. So the coefficient B will always stay as constant because the thin layer will not appear when all particles have already fully descended to the bottom. And that is what the PNK theory states. So I believe that's some misunderstandings in both of the opponent and also the reviewer, because B is always being kept as a constant. So therefore, PNK theory should apply. Next, how did you add the particles? We use PEI2, and the reason behind this is because that after crystallization, all the particle mass will stay at the exact range, and it will always become sealed in that container in which we basically shape it and we put it there. So it is always contained, so we did not have to add in the middle of the trials. So did you consider 1 minus C to the 5th power? So yes, we actually did. However, if you consider 1 minus C, that is going to be 0 point something, and if you times it to the 5th power, it will be as small. That can directly be neglected. So although we recognize that that is actually important, but yes, it is too small.
Okay, fine for Julie, ask question. Any question or comment from you?
For the before the you have said you were discussing many related to the terminal velocity, not to the initial.
Yes.
So is there any proof for this data?
Because throughout the process, we did not consider the velocity at the initial rate, because at the initial it will always be changing due to the global convection that is going on. So from PMK theory, we know that we can only consider terminal velocity, as terminal velocity is always being kept as a constant, and it will only be applied so that PMK theory is valid. So yes, only terminal velocity is considered.
So how about component?
I remember that I asked the reporter whether the velocity of the particle is constant, and the reporter replied that it's not constant. And we think that we also think that it's not constant because convection will cause the velocity of the particle to change. So it is not just described by the Stokes-Stanley velocity.
I do agree with the opponent that the velocity would change, and I think that the particles which, when its convection is come to close to the bottom of the tube, the velocity should increase.
Now here we iterate about the time sedimentation, right? I always wonder why the V0 is 1.
Oh, D0 is actually terminal velocity. So yeah, sorry for the labeling. It is actually the terminal velocity. Yeah, so that's why we have this right here. So the D0 is actually VT. So sorry for the labeling. We basically apply Stokes law, and we bring Stokes law value, which is a terminal value, in terminal velocity back into the PMK theory. Yes.
Terminal velocity.
Yes, this should be terminal velocity. Because velocity will be always changing throughout. Velocity will be always changing throughout the experiment until it reaches terminal velocity, because there will be a global convection going on, which is speeding up the process. So we have to find a point that it finally reaches the terminal velocity. Yes.
So means the same.
Yes.
Before it the final one.
Yes. Yeah. So what the equation will look like for the velocity is actually this. So it will basically approach a straight line because it is reaching terminal velocity, because it finally compared with when it minus the drag force, it will actually be 0, because initially it will be speeding, and then when it matches the drag force, it will equal out, and then it will remain terminal velocity until it falls to the ground.
The video will show.
Okay, so just consider when you're dropping a ball into a long tube, a single ball. So it will initially gain speed, but then eventually when it reaches the same value as terminal velocity, as drag force, it remains terminal velocity. So it is basically the same. It is basically the same idea right here, but we're just minimizing the size of the ball into a small particle. So it decreases its velocity at first, but then it eventually reaches terminal velocity when its value equals the drag force. Yes.
We have no further questions, so it's a scoring time. Let's show a score of the reporter. 7, 8, 6, 7, 8. The score of opponent. 7, 8, 7, 6, 8. And score for a reviewer. 8, 8, 8, 7, and 7. And thanks everyone for the second step. So we'll have a 10 minutes break. Everyone, now let's start our final stage. So opponent, you can challenge a reporter.
We would like to challenge problem number 10 from length disclosure.
Problem number 10. 10 seconds, we're going to begin.
Will you accept?
Accept. Team leader, please write the representative on the blackboard, please.谁是发言人？谁是今日发言人？你去帮忙一下。当我接线上。怎么样？不然你去找那个学生生。他们刚刚有换电脑。OK， 好，那个电脑是旧，可能是太新了，那个主看不批的。那这里就是那其他的先做一下。 Porter, start your presentation.
Okay, honorable judges and fellow competitors, this is a reporter from Senior Level Junction. I will be reporting problem number 10, droplet explosion. This is a public statement. Basically, when a droplet, water mixture droplet is deposited on a hydrophobic liquid, fragmented into different sizes of droplets. And investigative parameters that will affect the phenomenon. We believe that the key questions are what the causes of fragmentation are, and the relevant parameters affecting the size of the fragment. This is our structure. Basically, we first have an overview of the phenomenon, we explain the phenomenon, and we discuss our experiment. Lastly, we reach our conclusion. This is our phenomenon demonstration video. As you can see, the mother droplet will fragment into smaller droplets. This is the same experiment with high concentration. Yeah, this one. If that's the experiment with high concentration, the fragmentation is like actually smaller, the droplet will become smaller, and the explanation I will provide here. Okay, the phenomenon definition. Now we define the phenomenon. We define the radius of the mother droplet as such. The mother droplet will be the big droplet here, and the daughter droplet are the little droplets outside. We can divide the phenomenon into different phases. This is the spreading phase, in which the mother droplet spreads when no daughter droplets are created. And then the pulsation phase, in which the daughter droplet starts to form. And then lastly, the mother droplet will shrink, and then that's called an atomization phase. This is a phenomenon explanation. So first, we can reasonably assume that as we go from the center of the mother droplet to the side, the height would decrease. And we can also reasonably assume that the evaporation rate will stay relatively constant for a short time. Therefore, we can calculate that the concentration at the peripheral will be higher than the concentration rate at the center, which creates a concentration gradient. As you can see, there are relatively low concentration at the peripheral and relatively high concentration at the center. According to Marangoni's law, concentration gradient results in a surface tension gradient, which is the spreading of the droplet. If initial condition phi1, which is the concentration, is greater than phi2, then the concentration gradient will be greater, and that will lead to an internal velocity of the droplet being greater. So as you can see here, the concentration is greater. We have a greater velocity here. Then we can explain the forming of the daughter droplet. There are two forces in action here. First, the outward force, which is the flow spreading caused by the concentration gradient. Secondly, inward force, which is viewed globally, the surface tension tends to want to minimize the surface area. Then we can explain the pulsation. According to Plateau radiating stability, when the water is streaming out the mother droplet, the radius of the stream is not uniform, and then according to Laplace equation, the pressure difference would cause it to do this. So as you can see, due to perturbation, this stream, which is like radiating out the mother droplet, will not have uniform radius, and then it causes a difference in pressure, which then lead to the liquid flowing this direction, and that way it forms the daughter droplets. Yes, and we can see the atomization phase, and you can see with the higher concentration, we have a smaller daughter droplet, and with lower concentration, we have larger daughter droplet size. And we can now define the size of the droplet as the area of the droplet between the top. Yes, and then we can also note that there is an interesting phenomenon, which is that the daughter droplet form will have they have different sizes, and we will explain that later. And they also have different distributions. So our explanation for the non-uniform size of the daughter droplets is due to the collision of the daughter droplet and the non-uniform of radial, the non-uniformity of the radial flow. This is our experimental setup. We have a camera, like we're being used as a pipette, and we lock it to 10 micrometers, and we have a camera 25 centimeters above. We have a petri dish, and our distance of the pipette tip and the oil is extremely small, so we can avoid evaporation due to the dropping of the liquid. We also try different liquid water mixture. This is our radius time graph for IPA. And as you can see, the total time for it to reach atomization differs for different concentrations. And we can observe the non-symmetric nature of the curve. So this here, we have it takes more time to reach the maximum radius, then it goes back to the atomization phase, which is explained by detection of overthermal. This is the maximum radius versus concentration. We can observe that maximum radius is proportional to concentration, and as concentration goes higher, the concentration gradient increases, which increases the outward flow velocity and keeps the maximum radius to be higher. This is total time to atomization. We can also observe that total time is proportional to concentration. As concentration goes up, the outward velocity goes up, the maximum radius goes up here. This is the final size of droplet for IPA. As you can see, for lower concentration, we have larger daughter droplet size, which is in line with our theory. We also did other liquids, such as ethanol, and this is the demonstration for 70% ethanol and 85% ethanol. This is our RT graph for ethanol, which is, so as you can see, this is a similar trend, which takes more time to reach maximum size than it takes the time to reach atomization. Yes, and we can see the maximum radius and concentration is still proportional. We have the same reason. As concentration goes up, outward flow velocity goes up, and the maximum radius goes up. This is ethanol total time. And as you can see, there is an interesting pattern. It goes up and then down. And our explanation for that is like, as we go from like low concentration to high concentration, our evaporation rate increases since we have more alcohol in our mixture. Therefore, the shrinking of the volume cannot be ignored, which then leads to the total time decreasing. This is the final size of the daughter droplet of ethanol. It also follows a similar trend. As we have higher concentration, the sizes of the droplet decreases exponentially. This is our conclusion. The spreading only occurs at initial concentration greater than 0.65 for ethanol and 0.35 for IPA. It is the evaporation and concentration gradient that induces airplane flow with like spreading. Spike is a result of outward flow and the surface tension of the whole droplet. Pulsation with smaller daughter droplets is a result of plateau mixing. Maximum radius and total time is linear to the initial concentration. High evaporation rate will also significantly reduce total time. Statistical size of the droplet exponentially decays as concentration decreases, and statistical size of IPA daughter droplet may be less than 11 times. Thank you.
Okay, so I would like to ask you some questions. So first, can you please give me the so you stated that there are 3 stages. Can you give me the names of those stages? 3 stages.
First, there is the spreading phase,
Uh-huh.
and then pulsation phase, and then admin phase.
Okay, the next one would be, do you think that the boundary of the prejudice would have your result? Yes or no?
Maybe, but we did that dot is very small. It's not
Okay, so we only did one drop, right?
Yes.
Okay, so the next question was, do you think the viscosity of each liquid would affect the result?
Yes, but I think the main parameter affecting the result is
do you agree with me that there might be different sizes of final droplets in a single experiment?
Yes, I did explain that.
Oh, okay, yeah. I mean, like one single drop, there might be resulting in different final droplet sizes at the end.
Yes, I did explain that, which you can like.
Okay, and then can you please explain what maximum radius is?
Maximum radius is for the droplet because it expands further.
Yeah. So how do you define that maximum radius? Like when do you think it reaches the maximum?
We use software analysis
Oh,
to find the frame that is largest.
So just like right. Okay, then that's it of my questions. Thank you.
Paula, please start your presentation.
Hello everyone, my name is Typt and I'm from Team Typt, opposing question number 10 droplet explosion. So first, let us go into the problem statement. So we know that here we should make a water mixture, and then that we should have a hydrophobic liquid, and then we should investigate the fragmentation and the size of the final droplet. So that's what we're going to talk about: the process of fragmentation and the size of the final droplet. So the reporter, in summary, he had so for the phenomenon, he said that there are 3 stages of the fragmentation, including spreading, pulsation, and atomization, and then the concentration gradient was up. And then he also talked about concentration gradient, and then he also talked about how the surface tension affect the smaller droplets to go decrease in its thickness and then turn into smaller droplets. And then theory, he used plateau-related stability, metabolic effect, and less. And then experiment, he used different water mixture and different concentration. So here are some pros and cons of this summary of the report. So he had clear explanation of the experiment and equation supporting the had clear videos to observe the phenomenon, and then also he had the experimental setup. But the part of his, the question of his some report was that some graphs were not well labeled, and we could hardly see what it's talking about. And then there are also multiple errors that should be considered, which we'll talk about later. And then there's also experimental conditions not clarified, and then there's also some terms not being defined what we think are clear enough. And then he did not mention about the exclude a mixture in oil surface and did not quantify the result. And then also we are not able to, so now we're talking about points to discuss. So right here we have phenomenon explanation, which is so according to the problem statement, we know that there's a necessity of using a hydrophobic liquid, but according to their, I don't think we can see enough explanation of why we have to use a hydrophobic liquid in this particular experiment. And then also, what is the function of water mixture? The function of water mixture was not really stated clear in his report. And then also, the process of fragmentation includes like why does the fragmentation happens, and then the phases involved, and then the changes between those modes could also be discussed later in our discussion. And then the final droplet, that would be how we should define what a stable status is. And then the theory he used, so we would like to also discuss the boundary conditions, like size of the container and concentration. So he did give some experiments on that, but we believe that there would be like maybe comparing the theory and then also by calculating it and taking it into experiment to compare it and then see the boundary condition actually fits the theory as he gave some equations towards it. And also we think that this report lacks the prediction of the final droplet. So for the experiment method, so first, we believe that the measurement of final droplet was not clear enough, as the opponent agreed with me that there would be different sizes of final droplets in one single cartridge. So we believe that there would be more things to discuss on how we should define the final droplet size. And then also the effects of, because we can see that in some cases he used food color, and then we would also like to discuss the effect of that food color, because I wouldn't say it's completely just mixed with water, right? So parameters. So he did. So we believe that there are some more parameters that we added into the report, which are these, and maybe we can talk about it later. So now moving into discussion, can you please let's start with some defining problems. Can you please start going into page 16? Page 16. Sorry. So from it's probably 18 years old. Actually 17. Sorry. So here we can have. So it says that we can clearly define the size of the droplets, area of the droplet from the view from top. However, we can see that there are actually different sizes in these droplets. So I am not really sure how you did to quantify those results.
Okay, so how we quantify the size of the front droplet was that we statistically determine each, so like this is the frequency of the droplet being 0.2 in area, and so we took the mean of all these different.
Oh, okay, I see. So that's for all the experiments, right?
Yes.
Okay, then okay, I do agree that that's a good thing to say, but do you think then can you please tell me like why do you think there are the different droplet sizes? Like for example, why does the biggest exist, and why does this one exist also? Because there seems to be a really big gap around here, so I would like to get to know why.
If I explain this in this slide, so it's basically because the collision of the daughter droplets in a video demonstration.
Oh, okay, so the collision would be. Oh, okay.
Yes, they combine. But however, that is like not really big. So we use this as a way to show
But
that.
then why would I do agree that there are collisions of the droplets, but for example, why do you think the collision happens? Is it because the boundaries of your cartridge, or is it anything of that? It may be like an explanation why you think this would happen.
I think it might be because of the radial flow of the droplet coordinates. The velocity of the droplet at the time will actually catch up with the daughter droplet at the time.
Oh, okay. So do you think that this
they naturally want to like I don't know, gravitate together. Sometimes when they are all in a bunch, they just
Yeah,
naturally.
so in that case, how would you define like stable? So you can see that there's no clashes in your last stage of your experiment. But how would you define like stable and how do you define the final problems?
Do you mean like what time did I calculate my final size?
Yeah, yeah.
So we actually did that like right after the atomization phase. So right after the other problem disappears. And
So
we did like realize the problem that they might combine and that would affect the final problem size. However, that effect is not really big. That seems to be just, it's not really clear, but it doesn't happen really fast.
yeah, I know there are like I do agree that there are so many effects, but I think the problem here right now is if we can define this as the final problem, because there's no movement in here, so I hardly believe that we can define it as a final problem, because maybe we can really think about how we should define what's stable.
Okay, but how would you suggest it? Like how I can calculate the final problem size? Since it will always collide, it will always change. So when do you think it will be stable?
So I think by that I think we maybe you can use like maybe use like just to view it longer, like view it in a more and well like comparing multiple experiment and then define like where does each of the experiment of the final problems happen. So well then we can go on to another question. When do you think like different stages should happen?
Sorry.
Like in what conditions would different stages happen?
In what conditions do
Yeah.
different things can happen? Under the conditions in my experiment, they can happen.
Yeah, I mean like physical estimation, for example, when the surface tension of the
Okay, so in the first phase, it's red because the surface tension is red because the surface tension cannot hold the liquid together under gravity and normal force. And then in the second phase, pulsation is because of the concentration gradient. So it pulls outward, and also the force of surface tension which wants to minimize the surface area. And then the atomization phase is when the droplet just reaches area, zero area. Because it's just complete like continually straight.
Then do you think like the hydrophobic liquid that we use right here would cause any impact on this?
Yes. Like there will be interaction between the water mixture and the hydrophobic liquid.
Yeah.
And the main purpose of the hydrophobic liquid is to provide a surface for like a low interaction surface for the water mixture to create
So
concentration.
in that case, we need the surface tension that is right here. But according to my knowledge, surface tension should viscosity should also affect surface tension, and the temperature is used which has a boundary on top. Boundary should also affect the surface tension on the like boundaries of the temperature. Do you think that would affect your experimental results?
Yes, I do think that maybe that would affect. But however, the petri dish, the boundaries of the petri dish are really far away from the mother droplet and the daughter droplet. So maybe the flow will like have an insignificant effect, but the effect would be.
So about the question that you just asked me, for example, like how we could stop the flow, so like define final droplet. So you said that the flow might be created because of the boundaries of the petri dish. So I believe that maybe we can just use try to use a really big platform without the boundaries, so that the flow would stop according to what you said. And then okay, we can go into we can go into a next problem. So do you think that your theory can predict the size of your final droplet?
We can predict that it will how it will change relative to different concentrations. We cannot quantify that.
Oh, okay. So because I didn't quite see like a comparison between your theory and your experiment. So I think maybe that's the way to
the food color doesn't actually like dissolve in humid, since there are more alcohol in water. So that would definitely affect the phenomenon. So we decided not to use. We have half our experiment without.
Oh, so we have two colors that show, and then the graphs I suppose we use here are all without.
Without, yes.
Oh, okay. Then from here, it was like for example for these. So I see there's hardly any error bars.
Oh yes, if you come closer, there's actually a bar
Yeah,
here.
I know. I
Yes.
can see that there's probably error bars, but I just want to ask, what do you think the error comes from?
Under like lower concentrations.
Yeah, yeah.
I don't really know. It's actually an intrinsic problem. It's like you have to be higher here, and that is very small.
So what it might actually be like, for example, if the water, so for the error bars, if the water, the concentration of the water, so if the concentration is lower, you might have a slighter difference, a smaller difference between surface and gas. So like it would also it would also affect like the evaporation rate or anything like that. So that makes it that makes the error bar quite bigger than the
I don't really see how that affects your.
well, as you said later on that there's also when it reaches higher result, there are also evaporation of the ethanol, right? So I believe that the evaporation of ethanol here might actually affect the droplets of the.
Yeah, but like follow your reasoning, I think like the intuitive way of seeing that would be like maybe higher error there, since we have higher concentration, so we're on more evaporation.
Yeah, there's the difference between the evaporation and not evaporating, because
Time's up.
so we in our discussion we basically discussed about the phenomenon, like for example under what conditions would different stages happen, and also like the necessity of hydrophobic liquid, and then we also discussed about some other boundaries and also some improvements to be made in the presentation, and then also we discussed about some other definition problems, for example the experiment method, which the reporter also agreed with me that there might be some improvements to be made in the future, and then also we also talked about how error bars could be made, and then also how different parameters may affect the fragmentation. Okay, and that's the end of my summarization. Thank you.
If any honorable judges, that makes a question for the reporter. What is your main theory for the reason that the droplet is making polymers that contribute to the most?
Contribute to both. I think there's
What is the most?
I'm not sure the most. I don't know.
Well,
Do you mean like why is it happening?
so which theory contributes to the most that the droplet is expanding outwards?
I'm not sure about which theory, but I think you're talking about physical nature, and that would be the difference in surface tension.
Okay, thank you. So, what is your how does the surface tension between oil and the water mixture and the air interact? Yeah. Okay. What Robert?
So I think the air is more of an open space, so I don't see why you would
Yeah,
have
then how about
particular big surface tension.
How about a layer between the oil, the mixture and the oil?
Can you restate the all?
Okay, it's okay. Do you believe that the percentage of alcohol remains the same 30 years of surface tension?
So we try to control this by using that, which is like a very cold.
Do you think that distribution into the lower layers is important in the research? Because in your materials that you use for the experiment, it's actually materials that is endopattern, which means that it is both hydrophobic and both hydrophilic. So what do you think that would affect your experimental result?
We only input ethanol and
Yeah, because ethanol is endopathic, which means that it's hard resolving. Okay. What about
Can you state the question?
so there's mixtures that's actually endopathic, that is both hydrophobic and hydrophilic. In the experiment, to what extent does it arrows the result of the experiment?
So I believe that using viewing, so the oil actually fits into the water, mixed into the water, right? So I believe that while the hydrophobicity statement is a lot bigger than the other ones, so I think it would make it final difference.
Okay. How would you define the end of atomization, since that you stated that there's collision and the final Doppler size is not being defined and is constantly changing?
We did define our final Doppler size at the start of the atomization. And we are not concerned with the end of the atomization.
Time's up.
Okay. Good evening, honorable judges. I'm the reviewer from and the problem statement states that when a drop of water mixture is being deposited in the hydrophobic liquid, and the fragmentation of the liquid will happen. So our key points to the phenomenon is hydrophobic fragmentation and final droplet, and we have to define final as that there's a rib that is being completely broken down, that there's the smaller droplets are being outwards. And the overview of the reporter. So advantage of the reporter is that the overall presentation is very logical, and he clearly understands the problem statement, and some definitions are very clear and easy to understand, and the theory that is being used is also well coherent to the problem statement. However, there's some important parameters that are being neglected or not being considered in the experiment. And there's some lack of theory to the dissolution and the validity of the solution. And there are some terms that on the graph that is not being defined. And however, there's also like the final droplet, which is the key to the whole problem statement, is also not being defined. So we're not really sure how the result will change. And the advantage of the opponent, she clearly managed his time very professional, and he grabs on very important experimental errors, and she sees the important errors that is happening in the experiment, and she also clearly understands the problem. And some suggestions that sometimes she asks for the sort of relevant questions that is being already explained, and is another waste of time. And it doesn't point out the significant errors that lies on the reporter's report, and didn't go enough to and further extend on how the theory part didn't point out the lack of disillusion or the felicity. And she needs to ask a grasp on the topic that she sometimes asks some topic that is trivial or not important. So for discussion, the opponent asks, how did you quantify the size of the final droplet? That's each droplet size varies consistently. And so the reporter answers that we take the mean for the sizes of the droplet. We believe that the mean of the droplet is sufficient enough, but however, due to the fact that the final droplet size is always varying, that they couldn't define which process is at the end of the final droplet, such that they shouldn't take the mean of the size of the droplet at that time, because they didn't even know that the whole process is ending. And for discussion 3, how did you define stable as they were colliding? The reporter answers that we measure the droplet size right after the structured droplets detect. So we completely agree with the opponent that the definition of final droplet size is really unclear, that we don't know when the process is ending. We suggest that he might be viewing the whole longer process that to understand when it will end. And for discussion 4, do you think your theory predicts the result? And the reporter said that he couldn't quantify the results. So considering the probability that might give them theoretical results. And for discussion 5, then why are there little to no error bars? The reporter answers that the error was small enough. However, this question is quite trivial, that there's no need for decision.
I'm sorry.
Thank you.
This
is the reporter again, and I'm going to address my concluding remarks. First, I would like to clarify some points which the opponent and the reviewer seems to have understood. Firstly, we measured the size of the daughter droplet when the mother droplet disappeared. So we had a clearly defined time at which we measured the experiment. And also, our stages are clearly defined. During the expansion phase, the radius of the mother droplet increases. However, the daughter droplets have not been created yet. Pulsation phase is when the daughter droplet starts being formed. And the ionization phase is when the mother droplet shrinks and disappears. And for all our experimental data, we do not use food coloring, it is only for presentation purposes. And lastly, the Petri dish is much larger than the boundary of the effect, which is 10 times bigger. So the effective boundary is really small. Using a very large plate is unnecessary and would use up a lot of wood.
reporter review of the opponent. Now it's the time for Jerry to ask question. Professor Lee.
I asked the question, how to define hydrophobic and how to choose the surface.
So we choose a surface by we choose a surface for minimal interaction between the surface and the water droplet. Since the purpose of the surface is to provide an environment for which the concentration gradient can be formed, so that we can experimentally observe the phenomena.
And how to improve this? Why you choose the hydrophobic?
You mean how we
Yeah. The material is there.
we have chosen a lot of different materials, like you can see here we have variable and other things, but we did too much experiment and we don't have time for all of it to be presented.
So we cannot prove
What?
the material is hydrophobic.
I think our purpose is not
Yeah, the question we should select the surface of hydrophobic fluid, right? Right?
let's see.
Yeah. Hydrophobic.
Yes, says we deposit water mixture on your hydrophobic liquid. They ask for a definition for hydrophobic liquid.
But then in given food, material that hydrophobic, right?
Oh yes. Yeah. I
But then the reviewer and the opponent didn't find this question, right?
We have no further questions from jury, so it's a scoring time. Now it's time for jury to show the score. The score for the recorder 7, 6, 7, 8, 7. Score for the opponent 8, 6, 8, 7, 8. Now the score for the reviewer 8, 7, 7, 7, 6. So now it's end of today's business class. Or it says everyone. So do we have any comment from jury? Oh no.
老师可以讲中文吗？所以你要讲中文。OK。我觉得这个比赛很好啊，但是其实这个比赛不是要去强调说你做的多好，而是每个人在每个人的角色上的扮演。他 reporter 他做的很好，可是他一定有缺点。reporter 就是去抓他的缺点，那 reviewer 就是要把两个都没有做好事情讲出来，对吧？人家他有缺点，就要一直打下去，但是不是要吵架，我们是要把这件事情去懂我意思吗？所以有些时候老师在评论不是说完全是按照他的报告来给分，而是你有没有扮演好这个角色？我觉得这件事情是很重要的，对，而不是为了说只是说要把这东西呈现的很好，对吧？他做的很好，但是一定会有缺点的地方，那你要去把它指正出来，这样才是重点。个人的见解是这样。
今天大家表现的都不错哦，那不过有2点啊，希望可以对大家有些帮助哦。我看刚刚3组的这个 review 跟 reporter 啊，那个图的 XY 轴事实上都不是很清楚，可能最后一组的字比较大一点。那其实这个的话，很多时候图如果画得清楚，人家老师一眼看过去，感觉就有。不然就看半天，然后一定要跳到下一个，这个其实蛮吃亏的。这个希望大家可以修正一下。另外就是，其实大家的英文都不错。那可能有些同学的话，在报告的时候，那可能真的英文太好了所以讲得很快。那其实我想物理的话讲清楚，然后用比较少的字，有时候反而还是比较有利的。讲了半天，然后话就含在嘴巴里面其实那个或许你懂了，但是其实讲不到的所以这个可能跟大家这个建议一下我想刚刚有几组其实讲话非常清楚，非常大声但是还是有些同学呢应该建议是要再放大声有时候那个讨论的时候我想这个也是抢分的一个建议因为基本上评论是我们不是你们同学。 所以最好是面对着我们这边讲，啊，这个对你会有点帮助。今天大家用那个黑板用比较少，因为以前常常有时候一开始到黑板，然后人就遮着，然后在那边讨论，两个在那边讨论得很高兴，我们都不知道你们在干什么。啊，不过今天比较没有，啊，但是我想报告的时候，尽量面对着老师，声音也会比较清楚一点。啊，那真的建议不要就是一股脑想着讲很多东西，只要讲很多东西，点都没敲到都没分。哦，所以反而是讲清楚比较重要。
我是希望同学们在做解释的那些理论能够了解的更清楚一点啊。例如说第二组那时候，不是第二个 stage 的那个 random number， 我本来想要问，可是我自己对 random number 也没有那么有把握啊。你不是在一个 uniform 的 liquid 的，然后你又有non-uniform 的有粒子，又有那个流体啊。那时候 random number 是什么？啊，我觉得我如果问了，可能会答不出来。像刚才第三个 stage， 他是讲 concentration gradient， 那是别人的理论，你不可能是你去量的，可是你没有把握，我觉得你要是提出来，别人确认你的话，你可能就讲不下去了。所以就是说你有些理论很分析了，可是你没有搞得很懂的话，就避免不要。
昨天挺好的时候呢，就是有些同学讲话真的很小声，都听得很清。然后他们通过的时候比较少看。
好，那我们谢谢这个几个 jury 的那个 comment， 还有也谢谢大家的参与。那大家今天希望有一个比较好的睡，然后我们今天比赛就到此结束，谢谢大家。